Okay, so we're going to look at problem 10.16. So this problem is a combination of problems from chapter 10 and chapter 5. So we have a motor, 115 volts, half horsepower, 8 amps, has a code K rating. The efficiency is 75%. It's a single phase. It's connected to an electrical panel 100 feet away. The application environment's a manufacturing environment inside a manufacturing plant, right? We're going to use conduit. Okay, we're going to use some type of conduit to run this wire in. So what we want to find is the conductor type, size per ampacity, size per voltage drop, the locked rotor torque, so the max current during a locked rotor scenario. We want to find the voltage at the load, and then the voltage at the load when it's a locked rotor, and power factor. So we're going to run through a couple different parts of this. So looking at the conductor type, it is a manufacturing environment. It is in conduit. When we look at our types of conductors and we look at running things in conduit, we're going to use this THHN, okay, for conduit, for use in conduit, dry and damp locations, okay. So we use a THHN. And then, so we have THHN. We're going to have two conductors plus a ground. It's 115 single phase. So we'll have two conductors with a ground. So we'll actually have 3 wires, right? And we'll go with copper, okay? Copper is what we'd use for cabling to a motor, especially at that amperage, okay? We only start using aluminum when we start getting really high amperages, which start allowing our gauges to get a lot higher. So what is the size? Okay, what is the size of the gauge per amperage? So we have to look at what is the current, okay? And if we consider from chapter 10, we want to look at the conductors, okay? We have one motor, okay, so the current, full load current, is 125% of that is what we want to use for our ampacity rating. So we need to take whatever the current, full load current of the motor is, multiply it by 1.25, and then we can look at our ampacity charts from chapter 5. Okay. Now, the other thing that's very important when we start talking about, so let's put this down. So this current that we're going to find is going to be the full load current times 1.25. What current do I put here? What full load current do I use? Be careful. We don't use the full load current from the motor nameplate. If we remember back to the video slides, the NEC requires that we use currents, full load currents from this table. Single phase motors, table 430.248. So we have a half horsepower motor, and we have 115 volts, so we have 9.8 amps. Okay, so we're going to use this 9.8 amps in our equation. Okay, that's at a half horsepower. I know that's a little small, but that's from that table. So then we're going to put in 9.8 amps times our 1.25, and we get out 12.25 amps. So now we can look at table 5.5, and we can look at the 12.25. Of course, we need to go up to a 15 amp. Okay, and then looking at the THHN, we're at 14 gauge. We up rate to 15 amps, right? THHN, we have a 14 gauge conductor. So we'll have per ampacity, we'll have 14 gauge THHN. What about voltage drop? Now we've got to be careful. Voltage drop, we have 100 feet between the motor and the electrical panel. We also want to account for the 10% for connections, right? So we're going to take our length, our 100 feet, multiply it by 1.1, right? Of course, we get 110 feet. So that's the number we want to use. We want to go to table 5.5 again, but now we're going to go to the right side of the table. Okay. We also need to remember that we're going to still use the 15 amp row, because that's what we use to find the 14 gauge for ampacity. Okay. So we come back to this table. We're still on the 15 amp row. Okay. And we want to be 15 amps. We come across to the voltage, 2% voltage drop. 100 feet's too short. I need to be at the 125. So again, we're always rounding up. So I'm going to actually be at this 6 gauge based on my 2% voltage drop. Okay. So I'll go back. And I want to use 6 gauge to get my 2% voltage drop. So if I have the choice now, I want to use the larger of the two. Okay. Now what are we going to do for our locked rotor current? Okay. So now we're looking at the maximum current that we could see on this motor if it locks up. And so looking at our locked rotor current for a single phase, we have our M code times P, the power, divided by voltage. Okay. Looking at table 10.4. So if we go to table 10.4 and we pull up the K code, which if we look back up at our problem, we have a K code. That relates to anywhere from 8.0 to 9.0 kilovolt amps. We're going to go with the max, and so whenever we do this, we always go just below the max here. So instead of 9.0, we're going to actually put 8.9 kVA into our equation. Okay. So we put our 8.9 kilovolt amps, and I'm going to write that in as 8,900 volt amps. Same thing. Instead of writing kVA, I'm going to write 8,900 volt amps. Okay. Multiply that by my 0.5 horsepower divided by 115 volts gives me 38.7 amps. So this is the locked rotor current. When if I lock that motor up, that's the amount of current that's going to be pulled, or the motor's going to draw during that locked rotor scenario. So now let's move down to what is the voltage on the motor, on the load. Okay, it's 100 feet away. I've applied 115 volts from the panel. What actually gets applied to the motor after I drop voltage over the conductors? So my voltage drop at the load equation, or my voltage at the load, is going to equal the source voltage minus the voltage drops in the line, right, in the conductors. I know that my source voltage is 115 volts. To determine my voltage drop, that is going to be my current times my resistance of the conductors times my total length divided by 1,000. So, a couple things we got to be careful of here. we're going to put the nameplate current, okay, the 8 amps. So we're going back up to normal scenario running at full load. Okay, we're not talking about locked rotor. So at full load, it's going to draw 8 amps. So to do Ohm's law, we want to use that full load amperage from the nameplate. We're going to multiply that by the resistance per 1,000 feet of 6 gauge copper. Okay, so that's 0.491 ohms times 220 feet. Why 220? Because it is 110 times 2, because I have 2 conductors, hot and neutral. So I divide that by 1,000. That's going to end up being my 0.86 volts. So that goes up here. So I'm doing pretty good. I have 114.14 volts at the motor. So this number right here, table 5.3, was where I got that 0.491, chapter 5. So voltage at the load is the source voltage minus the voltage drop in the conductors. Okay, now let's go back to locked rotor scenario. I have a locked rotor. Okay, what's the voltage going to be at the motor if it's locked up? Same type of equation. Same type of setup. Okay, to find my voltage drop, identical equation as above. The only thing that changes here is the current value, the value of current that I put in. So instead of the 8 amps, I'm going to put the locked rotor current, 38.7 amps. That's going to equal 4.18 volts. So 4.18 volts up here, 4.18 results in 110.82 volts on the motor when it's locked up. Okay, so again, I lock up the motor, the voltage goes down, the current spikes up, right? And we've seen this in the lab. Now, this is very helpful here, I believe. Power factor. How would I determine the power factor of this motor in this scenario, right? I have an efficiency rating of 75%. Okay, that's not power factor. To determine power factor, I have yet another equation. Okay, power factor can be determined by power in system divided by current times voltage times efficiency. So we have an efficiency term. Okay, that's a decimal value. That's the 75% up here. Okay, that's that 75%. So power, what's the power? Another way to determine power or look at power is the horsepower and convert that to watts, right? So watts is a unit of power. Horsepower is also a unit of power. But we want this in watts. Okay? So I can take my 0.5 horsepower, multiply it by 746 watts per 1 horsepower. That's my conversion factor from horsepower to watts. Horsepower cancel out, I'm left with watts. Okay? Because I like to do electrical equations to get the power factor with watts. And then I look at, the bottom is my current, my voltage, and my efficiency. Okay, so again, I'm going to use my 8 amps, because that is my full load current that I'm actually drawing from the motor. Then I'm going to do the 115 volts and my 0.75 efficiency. And that's going to come out to 0.54. So a power factor of 0.54, which is different, right, than our efficiency. Okay. Now, I'd like you to also notice the top here is my power, right, in watts. So this is just watts on the top. The bottom here is my volt amps. Volts times amps times this efficiency, right? Power factor, another term, another equation for power factor, is watts divided by volt amps, right? So that's really all we're doing here. We're just adding this efficiency term because we're not 100% efficient. There we go. That's how we can determine what conductors to use based on ampacity or voltage drop, the type. We can look at locked rotor currents. We can look at voltage drops at the loads, locked rotor voltage drops, and power factor. Very helpful problem here.